This is my Lab 3 report for circuits. The purpose of this lab is to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. Some fundamentals for this lab is the conservation of energy and charge, the circuit laws, which include the node In equals I out, and loop rule, Ohm's law, which is electric current is equal to voltage divided by resistance, and the capacitance formula C equals electrostatic constant times area divided by distance. Some important things to note for this experiment is that the system is a circuit and its surroundings are anything else that does not pertain to the circuit. We utilize an online circuit model where we can assume that wire resistance is negligible and emitter resistance as well. However, this will become a source of error for us because in real-world calculations, resistance from the wire and emitter is greater than 0. Listed are results from the experiment. Here is a representation of the circuit given to us that consists of two batteries, two emitters, which are both equal to 0.02 amps, and two resistors, one being 47 ohms and the other 100. When in the presence of a voltmeter, delta V equals 3 volts, and in a closed circuit, delta V of the 47 ohm resistor is equal to 0.96. For the 100 ohm resistor, delta V is equal to 2.04. Here are visual representations for different voltages. The voltage for the batteries is 3, for the 47 ohm resistor is 0.96, and for the 100 ohm resistor is 2.04. Here is a potential difference diagram where we can see the battery helped the voltage reach 3, and as it moved through different resistors, the voltage came down. For part B of the experiment, we modeled a 10 and 20 ohm battery with a 9-volt battery and a 200 mF capacitor. We found that the capacitor's charging and discharging time was 29.6 seconds for the 10 ohms and 58.3 seconds for the 20 ohms. To your right there is a graph that represents the voltage as the capacitor discharges compared to time. A linear relationship is observed with the R² value of 1. Questions to consider for part A. When the voltmeter is attached, why doesn't the ammeter reading change? This is because the voltmeter has high resistance and there is no current flowing, which causes the ammeter reading to stay put. What happens when the ammeter is connected in parallel with the 100 ohm resistor? Both ammeters will read 0.06A. Questions to consider for part B. What happens to the bulb when a battery is connected in the RC circuit? The light bulb becomes very bright and will dim over time until it is completely turned off. What happens when the bulb is connected to the charged capacitor in series? The same trend will occur as described previously, where the light bulb will become very bright and dim over time until it is completely turned off. Some further understanding for the experiment. What if you were doing this lab in real life and use an actual emitter instead of an ideal simulated emitter? What's different about a real emitter and how would it have affected the circuits you hooked it up to? We would get lower current results due to the resistance of an emitter in the real world. Emitters typically do have resistance, so it is very unlikely for this situation to occur in the real world. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? How would this prediction happen in real life? The ideal model would predict the capacitor to be charged instantly. However, in real-world applications, there is resistance in the wires and batteries, so this would also be unlikely. Thank you.